Hello everybody, the topic that I will be talking in this video is about the states and operators in quantum mechanics. You know what, the subject quantum mechanics actually deals with small particles and maybe small objects like an atom or maybe a molecule. So let us take the case of simplest of the molecules, the hydrogen atom. It will have a nucleus in it, which I am writing as plus sign, and around that you have electron. And when the energy of the system is actually lowest, then this electron will be actually kind of can exist in a spherical kind of orbit, we say. So this spherical shape is actually what we call as state of this system at lowest energy. And this state function is actually, sometimes we call state function of a quantum mechanical system. We actually write as psi. And this same state function can also be denoted using Dirac's notation as ket psi. This is called ket psi, and this is called psi, the state function. And the state function can be altered. It can actually, the system can have different state function because of some operation. We may actually do something to the system, and because of that something, this system can actually have a different kind of state. So this psi, when we actually kind of operate by something called O, then it can be taken to a different psi, which I can write as psi prime. And that something which altered the state is actually called as operator. So operators are actually kind of mathematical rules which actually change the quantum mechanical state to a different state. So the topic which I can actually label here is, I'm talking about states and operators. State functions, we may say state functions and operators in quantum mechanics, So as I said, the state function will actually help you to find out the orbit of the quantum mechanical system, and the operators actually will alter these orbits or maybe these state functions. And in quantum mechanics, we actually care about some equation called Schrodinger's wave equation, and that is actually IH cut into dou by dou t of this state function psi, which could be a function of both spatial coordinates like x, y, z coordinates, and it can also be a function of time, and that is actually equal to h. We write this is called Hamiltonian operator of the system, and then psi rt. So this Schrodinger's equation is actually telling about the time evolution of the state function. And this operator h we are writing here, of course operators we actually put hat on top of them just to actually kind of denote them. So if you write something like hat on top of some English, capital English letter, then we should understand that we are talking about operators in quantum mechanics. So this h is actually called Hamiltonian operator. So what I'm saying here is the time evolution of state functions of quantum mechanics are actually governed by Schrodinger's wave equation. And this, let me go into kind of specific, let me go into saying that these state functions can be functions of coordinates. As I said, this psi can be a function of x, y, z and t. So it could be a function, mathematical function. And for a system which is actually discrete, for a system which can have only discrete states, like we can talk about spin of electron. So at that specific case, will be having a spin up or maybe spin down. So there are only two states. So in that kind of situation, the state functions, state function will be actually either 1,0 for up spin or maybe 0, 1 for down spin. So spins, a state function at that situation we are denoting as column vectors. So the state functions can be simple mathematical functions, or they may be also column vectors. So if we have a state function like a mathematical function depending upon variables x, y, z and t, then operators we usually have in differential form. So if you have the state function like this, then operators usually are actually mathematical rules. That means there could be something like dou by dou x, or they could be something like dou square by dou x square. So these are the kind of operators now. So if you have the state functions like mathematical functions, then the operators will be usually differential operators. And if you have state function like column vectors, then operators will be square matrices of same dimension. For example, here it is number of rows are 2 and number of column is 1, so it is actually 2 by 1 matrix here. So for this kind of a system, operators are usually like 2 by 2 matrix. Operators will be actually 2 by 2 matrix. These are state functions and these are actually operators. This is the thing. Eventually we worry about defining something called Hermitian operator, which is actually very useful in quantum mechanics, because all physically observable things like position, momentum, then force, energy, all those things are actually our Hermitian operators in quantum mechanics. Okay, we'll worry about that when we come to that topic. But for now, in this video, what I wanted to tell you is state functions are actually required in quantum mechanics, and they are governed by the Schrodinger's wave equation. And operators are also important, just because these operators, when act upon these state functions, they take to different state. And these state functions can be mathematical functions depending upon variables x, y, z and t. And operators at the time could be some differential kind of operators like dou by dou x, dou square by dou x square, or maybe del square operator, which is called Laplacian operator. And when we actually specify the state functions like column vectors, then at that situation the operators will be actually kind of square matrices. This is it I want to talk in this video, and I will meet you next time with some other topic. Thanks for watching. Bye bye.